Imagine capturing a tiny piece of a star and putting it inside a bottle right here on Earth to power a whole city. That's the basic idea behind nuclear fusion. The sun itself is a giant fusion reactor. It uses its immense gravity to crush hydrogen atoms together deep inside its core. Let's look at what that actually means. Nuclear fusion is simply the process of taking two very light atoms and forcing them to combine into a single, heavier one. But here's the catch. If you weigh the new atom, it actually weighs slightly less than the two original atoms did before they crashed together. A tiny bit of matter just disappears. That missing matter doesn't just vanish, it turns into pure energy, following Albert Einstein's famous equation, E equals mc squared. Even though the lost matter in each collision is incredibly small, the energy released is huge. A tiny amount of fusion fuel holds millions of times more energy than coal or oil. If we can figure out how to replicate this stellar process safely on Earth, we would have a clean source of power that could last for millions of years. You might be thinking of the nuclear power plants we already have. Those use a process called fission, which creates energy by splitting heavy atoms apart. Fusion is the exact opposite. The tricky part about fusion is that atoms really don't want to be pushed together. Because their cores are positively charged, they naturally repel each other, pushing away like the wrong ends of two magnets. To get the atoms to fuse, we have to push them with enough force to break past that invisible wall of electrical resistance. The sun uses its enormous crushing gravity to force them together. We lack that kind of gravity on Earth, so we have to use extreme heat instead. We heat the fuel to around 100 million degrees, causing the atoms to zip around so fast that they smash into each other. To actually use this to generate electricity, we need to build a controlled system that can hold on to a superheated cloud of atoms without breaking a sweat. When you heat a gas to 100 million degrees, it changes state. The atoms strip apart, leaving a supercharged, electrically active soup of particles known as a plasma. This creates a serious engineering puzzle. There is no physical metal or glass on Earth that can hold a 100 million degree plasma without melting instantly. This is a fusion reactor, essentially a magnetic bottle. Inside this donut-shaped machine, incredibly strong magnetic fields grip the charged plasma, suspending it perfectly in midair. Notice its capital D shape. This helps keep the highly turbulent particles stable as they swirl. Building these massive magnetic cages requires global teamwork. Right now, 35 nations are working together in southern France to build ITER, the world's largest experimental reactor, proving this design can produce significant power. The invisible bottle holding the fuel is just as vital as the glowing star inside it, demanding some of the most precise magnetic engineering ever attempted. So once we have our floating, burning star safely trapped in a magnetic cage, how do we actually get electricity out of it? It turns out a fusion plant is really just a highly advanced way to boil water. This schematic shows the energy flow. Fusing atoms shoot fast-moving neutrons into the reactor's blanket. The blanket absorbs these impacts, heating up rapidly. A fluid carries this heat to an exchanger, boiling water to create massive amounts of high-pressure steam. From there, it's a century-old process. That intense steam blasts through a large mechanical turbine, spinning a generator to produce an electrical current. Finally, that electricity travels out of the plant and directly into the power lines that feed our homes and businesses. We take the same reactions that light up the night sky, capture their heat, and use it to spin a mechanical wheel. Because this process is so difficult to maintain, it comes with a built-in safety feature. If the magnetic bottle fails, the plasma simply cools down, and the reaction fizzles out immediately. A runaway meltdown is impossible. The fuel itself, mostly derived from water and lithium, is abundant enough to last humanity for millions of years. And unlike older nuclear plants, fusion doesn't produce long-lived, highly radioactive waste. Beyond safety, fusion provides a structural benefit to our power grids. Because the fusion plants use massive, spinning, physical turbines, they provide a steady, reliable momentum to the electrical grid. This helps balance out the natural dips and spikes that happen when the wind stops blowing or the sun goes behind a cloud. It provides the stable 24/7 foundation of power that a fully green grid requires to stay reliable. To measure our progress, scientists use something called a gain factor. This is simply the ratio between the energy we pump into the machine to keep the plasma hot and the energy the reaction gives back. The ultimate goal is to reach a state called ignition. That is the point where the reaction produces so much of its own heat that we can turn off the external heaters entirely, allowing the plant to sustain itself. For decades, this felt out of reach, but recently, major research facilities like the National Ignition Facility have crossed that threshold, getting more energy out of the reaction than they put in. We are steadily moving from laboratory experiments to commercial engineering. Soon, we could see a network of these reactors providing steady, carbon-free electricity worldwide. After decades of careful research, we are finally learning how to bottle a star, bringing a power source that lasts for millions of years within our reach.